Well, good day, everyone. So this is, I think, the last of the kind of construction materials that I'm going to be lecturing on this term, and the final lecture next week will be looking at. Generally, we'll be looking at materials and how we can use them efficiently. So today I'm going to do this is a fairly brief lecture on structural glass. Just to start by saying that, I'm sure that most of you already know this, that the structural glass used in the construction industry has been toughened. It's not float glass that comes straight off the line from Pilkington's or Saint-Gobain. It's been toughened, and there are a couple of processes that are employed to do that. Most even kind of fairly small scale glass processors can have the capacity to do this, to toughen glass for you. So here's a factory. Actually, it's in South London. Funnily enough, it's not that far from where your campus is. Interesting material because, of course, it's incredibly strong in the line of the glass, but of course it's incredibly brittle in any other plane. So moving glass around the planet, moving glass around factories is an important is in itself an important process, if you like. And we've developed these fantastic suction machines. I had somewhere or another, but I've lost them. I had some photographs of when they were building the Shard, and these were predominant. They were poking out through from the floors with robot arms and attaching themselves to the facade on the end of robot arms, I should say. So here's this process of reheating glass to temper it, anneal it, and of course what you can do, even in 2 dimensions. You can cut and form glass into all sorts of shapes and sizes using CNC cutters, laser cutters. You can puncture it. So as a plane, you've got an awful lot of control over it. And this is funny again. Like a lot of the processes I think we've looked at, there's this only combination of using machine tools and using hand tools. What this gentleman is doing is he's using some kind of sandpaper, effectively, to soften the edges of the glass, to give the glass an edge. Now, what we're looking at here is a process where, if you want to then texture glass in any way, if you need to, for whatever reason, either to control solar gain in a building, or just for privacy, or for whatever other reasons, what you do is you take your sheet of float glass, whether it's been toughened or not, and you reheat it, and then you allow it to slump onto this whatever shapes that you make here. And these shapes, this is just plaster. This is a gesso material, simple material. That you make the shape, and then you slump the glass onto it, and it will take that form, whatever that form is. So here's a nice simple example, if you like. You can probably reckon already that this is a stair tread from a spiral stair. It's been tempered, so it's incredibly strong. It's also been textured, so of course that you don't slip on it, and as you can probably see, also the edges have been softened, haven't they? So all the processes have come to. Oh, and of course it's been laser cut to shape. So what do I know? There's 3 or 4 processes. Once the float glass has arrived at this processing factory, there are 3 or 4 more processes to go through before it arrives to you on site as the construction component that you ordered. So the other thing that we do with glass is to laminate it. Is to again, it's a process that I've mentioned a number of times through this series, where you're layering it up. This will stiffen it and strengthen it, even if you have already have toughened glass. The process of laminating will strengthen it further, and you're beginning now to get to a point where you can really take serious loads with the glass. The process of laminating means bonding pre-made glass sections together with an interlayer. And just as an aside, I suppose, you can laminate anything you like between layers of glass. So if you're interested in the texture of glass or in the way that it transmits sunlight into a building or light into a building, I mean, this is actually wax. This is 2 layers of glass bonded around wax. On the left we have layers of glass bonded around very fine cotton, and of course you can print onto glass, and it's a sensible idea to print onto the inside of the glass, so that when you bond it together, that print is permanently there. Whatever it is you've printed onto the glass is permanently there. I mentioned earlier this process of slumping. You will be familiar with the incredible complexity, geometric complexity that you can achieve by slumping glass, because you will have seen car windscreens, which take very complex three-dimensional geometric shapes. The process of slumping is that in this case, as you can see, it's 2 layers have been bonded together here. So it's it's a piece of laminated glass. As a flat piece of glass, it is placed back into the kiln, and it is placed on a formwork, just like with fibre reinforced plastic. For those of you that saw the lecture last week, you build a formwork, you sit the glass on top of that, you reheat it, and it literally slumps. It falls into whatever the form is that of your negative. It will take that. It will slump into it and take that form. So here we're looking at a piece of glass that's gone through a number of processes, as you can see. It's been laminated. Inside that lamination, there's been some printing going on, and then it's been slumped to achieve the final product. So here's a few little examples. Now you will see at the bottom of the screen, Glass Light and Special Structures Limited. So again, because the situation we're in, this lecture would normally be, well, hopefully would be given by Tim McFarlane, who is the director of Glass Light and Special Structures, and he's and Tim is a pioneer of structural glass, so he gives a far more interesting lecture on it than I do. His presentation is his previous presentation to your year group is available as a PDF file, and if anybody gets very interested in this this material, please do email me, and I will send you Tim's Tim's lecture. So I think this particular stair, bear in mind, remember, we're talking about structural glass. We're talking about glass that really can take load. It's not just a climate control material anymore. This is as a number of Tim's projects. So this is Eva Jerichner's project, and anybody that's familiar with her work will know that she not only is she very interested in glass, she's also very interested in structure, and she's very interested in lightweight, very delicate structure. And you cannot make structure more lightweight and delicate than by using elements in pure tension. So you'll see lots of steel rods that are doing the work of carrying this staircase. Here's another building by Tim McFarlane, and this is beams and columns, of course, or ribs. I suppose we should say ribs, but this is a pure glass structure. The only other material that keeps this building together is silicon mastic, which kind of glues the glass together. The joint you're looking at is a fritted. It's known as a fritted joint. It's a laminated beam here. There's a laminated rib. You can just about see it. I think there's 2 or 3 layers here of lamination, and they kind of slot together in this beautiful. It's what we used to call in joinery a finger joint, where you slot two elements together and then they're glued. So it's a very elegant structure. Not only is it just pure glass, but of course even the ribs here, even the beams are, we're not putting rectangular beams, we're minimizing the amount of, because look, the load of course is increasing towards the center and it's minimizing, so they're curved in section, which is beautiful, isn't it? Really beautiful structure. So this is the proof of concept, if you like. Tim, I know I keep referring to him. He often says when they were exploring the structural potential of glass, that very early on, what you do, of course, very simply to analyze it, is you drill a hole. You might just drill a hole and then load the glass through that hole. And what they found was that if you load glass absolutely in line with the plane of the glass, that it is stronger than steel in terms of that, in that plane. It's incredibly strong material. This is one of their projects. This is you can see it's cantilever. It's actually the entrance to a subway in Japan. It's a beautiful cantilever rib. This is another one. This is what we call a reciprocal structure, because it's lots of short lengths. Actually, these are stainless steel, little stainless steel connections that are connecting the horizontal and vertical ribs that put the building together. It's actually that. It's the entrance to the Apple building in New York. Although, funnily enough, it's not like that anymore, because Steve Jobs, when he was alive, he loved it. He wanted a glass cube as his entrance to his building, but then he said, "Oh, there's too many bits. Can we do it a bit simpler?" And any of you who've recently been to Manhattan will have seen that it now employs even less glass, and I'll get on to how it did that a little bit later. Larger components, if you like, than this, just large planers, and I'll talk about that in a minute. It is worth noting at this stage, if you're looking at building with structural glass, it's worth thinking that there's a maximum size, as with all construction materials, in terms of transportation. How do you move things around? We really have to think about this. And at the moment, you could theoretically manufacture a piece of glass in any dimension, but there's 2 reasons why we don't. One is the size of an articulated lorry, a truck that can move it from one place to another, and the other is, of course, that if there is if glass is subject to any decay or needs repairing or replacing, the bigger the piece, the more problems you have in replacing it. So we tend to make make frames around glass, and we tend to put them together in this old building here in kind of slightly smaller sections, just as an aside. So there's that lovely stainless steel connection detail where you bolt through the glass, and as I said earlier, they found that in that shear plane, the glass can take an enormous amount of load. And here's another, something for you to remember, I hope, is that architecture is very often, as Mies van der Rohe once said, I think, is in the detail. That you can design a reciprocal structure using laminated glass, and you can sort of draw a diagram of it. You can diagram it and show it at a certain scale, but when you come to put the building together, a lot of the architect's work is actually in that little node, isn't it? Oh, beg your pardon. So so I mentioned earlier that there's a point at which the laminations in structural glass make it possible to take enormous loads. And this building, which I think was completed in 2015, not that long ago, the glass that you're looking at here is a load-bearing wall. There's no tricks going on anymore. There are no other columns, so the roof is being carried by the glass, as you can probably see inside. It's just not some clever cantilever. There's nothing going on inside. The roof is being carried by the glass. So, you know, this is where we are now in terms of structural glass technology. It's a load-bearing wall, which traditionally would have been reinforced concrete, stone, brick, what have you, a generally lowish tensile materials. And here we are with the structural glass wall, which is really wonderful. How that's done, how the bonding of the laminate is done, is Inoplast interlayers. Okay, so it's composite. It's a composite material, and it's used. What's happening is that these planks are made with the same system. What's happening is that you're bonding in between the layers of glass. In fact, an acrylic. An acrylic is it's an acrylic glass sandwich. So what the acrylic is doing is giving the glass a kind of fail-safe mechanism in this case. Okay, if it's reinforcing it with it and preventing it from ever possibly failing. I mean, of course, what we're looking at here with the old lovely the spider fittings. So not only we have a glass floor, we have a glass wall. Here we go. Now you can just about see. I know you can see there's a very thin layer of acrylic in between here. It's been textured. There's the stainless steel fittings that deal with it. Of course, you can actually. There is a lovely old tradition of glass blocks, of actually stacking, of casting glass here. So we're not floating glass as you do when you're making a large flat glass panel. We're actually casting it. Again, it's a process that we've come across when we've looked at a number of materials, haven't we? You pour it into a mold. In this case, we make little glass blocks, and then you have to make some kind of frame into which they can sit. And there are various techniques for bonding them together, not unlike brickwork. There's steel in this one because it's as we know, we always need to, if you're making some kind of load-bearing structure, we always need it to have a good tensile to be able to take loads in tension. U-section glass planks. And I think this could be one of the last case studies I'm going to show you today, which is now. So okay, if you can cast glass, which you can you reinforce? Can you cast it in such a way that it is structurally inherently reinforced? When you're looking at this facade, this is actually, by the way, this is a building in Turkey. It's a fairly radical piece of technology. When you're looking at this facade, you're thinking, why is it? What's going on here? Well, you know it's been, it's triangulated, which is stiffening it. It's got the glass has a deep section, as if you were making anything that required structural strength. You have to look at the cross section of it, and of course, but there's no framing. This is a curtain wall. You can see it's a curtain wall because it's high. There's the floor. There's the roof, floor levels. It's pinned back. It's hung effectively from that floor to the ground floor, to that floor there, and it's pinned back. This one's hung from there. So it's a curtain wall. But of course, the problem we always have with glass, with any kind of facade, is lateral wind load against this facade, and therefore if it was pure glass, we'd have a series of ribs, wouldn't we? We'd have to deep section there, or we'd have to build a frame out of, what do I know, timber, steel, aluminium, doesn't matter. No frame. Big lateral load here, no frame, just silicon mastic to keep the rain and wind out, and the glass doing all the work for you. Isn't that lovely? So here's how it's slumped or cast. Mm? So, as an architect, what you're designing here is the tool that enables the glass to be cast. You're going right back in the technology in order to solve the problem, if you like, which I think is very interesting. Here they are being delivered to site. As I said, it's a curtain wall structure, and just to to sell, I suppose, the product. These are the it is now a product. So those are the manufacturers. So yes, as I said to you before, please do get in contact if you want to drill down into glass technology in any more detail. And thank you very much, and see you next week.